Hi, I'm Richard, Principal at Quantitative Management Consulting. I'm going to take you through the core of PowerOpI. I'm going to show you how to use Excel structured tables and structured references to hold data in Excel, how a database tool can query those tables, then how to pull the query result back to Excel to drive a pivot table or create a structured table result in Excel. I'll show this using Excel data connections and also Power Query and Power BI. I'll show an evaluation of differences between data connections and Power Query, and I'll show how to build several of the PowerOpI paths through the tools. You should review the PowerOpI workshop overview first for perspective. This channel will show more training modules showing greater depth, and they're listed toward the end of this module. Many of you are no doubt using structured tables in Excel already. Structured tables can be created on an Excel worksheet using the Insert Ribbon Table tool. The picture shows a structured table in blue and white formatting. You can edit structured tables just like editing areas on a worksheet. They have rows and columns, and the columns have names in the top row. In the context of worksheet tools, I'm going to call columns columns, but in the context of table tools, I'm going to call table columns fields, since we're going to use them with a database. You can use the pull-down in each field name to sort and filter rows based on row values in that field. You can use Excel ribbon tools for worksheet row and column insert and delete, or by using right-click menus on the worksheet. The worksheet row and column tools insert and delete whole rows or columns on the worksheet. If you move the cursor to a table row edge or field top, a selection arrow appears, red in the figure but black in real life, that allows you to insert or delete rows or fields in the table without affecting whole spreadsheet rows or columns. You can drag and also insert or delete multiple table rows or fields to reposition them inside the table. You can right-click inside the table to select tools to insert or delete rows and fields. You can also add a totals row at the bottom and choose from a number of functions for each cell in that row: sum, average, count, many more. You can expand a table on a worksheet by typing, dragging, or pasting data to the row or column just outside the table, shown in gray, or by pulling the little black caret symbol at the bottom right of the table. A table is sometimes updated by a linked source like a database, and if it is, the table resizes automatically to fit the linked data when it's refreshed. If you've deleted some columns in a linked table, it remembers that when refreshed. If you've added fields with row calculations to a linked table, those are kept on refresh, and expressions in them are maintained and copied into new rows. We'll talk about structured references next, but if you add rows to a table, structured references will automatically copy down to the added rows, simplifying table updates. Constants won't be copied down. Here's a summary of the Excel structured table operations we just reviewed. You can also name a table by clicking in it and using the Design Ribbon Properties field to set the table name. You'll use many tables for PowerOpI and for other applications too. It helps to name the table something like TBL allocation, which I'd pronounce as table allocation, and name its tab allocation so you can find many tables conveniently. You'll find it's a good practice to place one table per tab or worksheet. A little formality about structured references. When you add an expression in a table cell, you'll see symbols like those in the right column of the top table, full of brackets, @ symbols, and hashtags. These are structured references. Tables can also support cell addresses like A3 and B$25, but structured references introduce a location-independent way of referring to data. We want Excel to find its own way through the data in PowerOpI. That makes the solutions far more robust. I've defined PowerOpI in ways that make Excel find data automatically using names that are address independent. That eliminates bugs about referencing data, and you won't have to fix up addresses of linked cells when adding or deleting some capability, like a new hardware build or a rack element allocated to many uses. For the most part, when you get address-independent references working the first time, they stay working through thick and thin. It's worth the design discipline to use them. The top table describes structured references used on Excel worksheets. A field name in brackets specifies a column. If preceded by an @ symbol, it's the value of the named field in this row. Names are strings, even if you use numbers, so don't count on some numeric capability in field names. A field name containing a special character, like a space, has to be bracketed to be used as a structured reference. There are special names preceded by hashtag with pretty obvious meanings. Hashtag all, data, totals, headers. You'll mostly use hashtag headers quite a lot. The bottom table describes structured references when used in VBA. Structured tables are list objects. If you set a variable this table as a list object, then hashtag data in VBA is this table.dataBodyRange, and headers in VBA is this table.headerRowRange. VBA doesn't support structured references with the syntax used in Excel user interface, which is too bad because we'd like to use index match, SUMIF, and other capabilities from within VBA. But there's a training module that will be on this channel, and the website already has a discussion on it, that shows how to use structured references in VBA that are very similar to the same structured reference syntax that would be used in the Excel user interface. There are a few functions you'll use all the time to navigate a local table and foreign tables. In particular, Excel index match and SUMIF are essential. You may be using VLOOKUP already, and that does work with structured tables, but there are some limitations with VLOOKUP in any use. VLOOKUP searches only to the right, and the column number is relative to the search column, essentially a fixed address. We want lookups to be independent of addresses without constraint. Index match is a bit more complicated, but you do get used to it, and it provides complete location independence in every way. Here's index match stretched out a bit to show how it works. The outer index function specifies a from table to look in, and we use two match functions as parameters, one to search for a row and the second to specify a column of values. The match functions return a row number and a column number in the from table. The from table to be searched can be either a local table or a foreign table anywhere else in the workbook. IntelliSense will help you a lot typing out one of these expressions, keeping parameters straight, and suggesting values available. And in the description of index match I'm about to cover, the names in blue here aren't the literal values you'd use. Instead, you'd put in actual column names and search values you're using that provide the function named in blue here. So the first match is there to find a row with a specified sought row value, typically a key value that it's looking for, in a field named column sought in name in the table named from table. When such a row is found, the first match returns its row number in the from table. The second match looks across the headers row in the from table to find a field named as the sought return column name. Not literally sought return column name, but the name of the column you want the values from. When a matching column name is found, the second match returns its column number in from table. Then the index function returns the value from the from table in the row and column intersection specified by the matches. So we specified what to look for by using names, and Excel invisibly resolved those to the physical address of the values to be returned. The sought row value and the sought return column name could be literal values, but there are plenty of times they could be values computed or specified in a cell in the current row of the local table, so this is very programmable and flexible. Then the match functions also identify columns in a from table. That from table is going to be the same as the first index function parameter, from table. Technically, the table name in the matches could name a different table than the one to be searched by the index function, but that would be very unusual. The match functions identify the first matching item they find. If there could be multiple items that would match, a different lookup method can be used, Excel SUMIF or a database join. Index match returns the first matching item it finds. If there may be more than one matching item, and if you want to sum them, you can use SUMIF in Excel, or you could calculate in a database query instead, but a SUMIF is easier. If there may be more than one matching item, and you want to create a separate record for each one, you would join the tables using a database to do that. We haven't covered SQL database query and join operations yet, but they can add fields to a table and can also expand a record into multiple records. More on that later. So here's SUMIF, also stretched out a bit to show how it works. The SUMIF parameters specify a sought row value to be searched for in a column named column sought in name in table from table. And for each row found matching that, SUMIF adds up the values found in the column named sum column name in all those rows. Of course, the names in blue here aren't literal values to be used in the search. You would put the actual column names and search values that provide the function named in blue here. The first two SUMIF parameters specify criteria for finding rows matching a sought row value in a from table. SUMIF searches for the sought row value in a column named by the column sought in name parameter in the from table. Multiple rows may match that criterion. The third SUMIF, sum column name parameter, specifies the name of the column in from table that contains values to be summed in matching rows. SUMIF looks across the headers row in from table to find a field named by the sum column name parameter. When the column name is found, SUMIF adds up the values in that column from rows matching the sought row value criterion. Other if functions can also be used to aggregate values with similar criteria searches. Structured keys can be constructed to identify records that match criteria in several of its fields, giving great capability to index match, SUMIF, other if functions, and for database joins. By record, I mean table row. Fields in a source table record can be combined among themselves and with literal values, for example, the string CPU, to make a structured key, and making records self-identifying as matching several simultaneous criteria. Again, we want to search on values without using absolute addressing. In a source table to be searched, you create and name a key field to be present in every record to hold the structured key for each record. The values can then be concatenated to form the key value. It's useful to separate each value by a special character to help readability and avoid ambiguities that might occur because of unexpected letter sequences in the concatenation. The special character should never occur in any of the values concatenated to form the key value. Several possibilities are suggested. In my PowerOpI applications, I've been using the colon character, and I never use that character in any table data values. Here are some examples of expressions creating structured keys and example resulting key values. You might need to create some artificial values to differentiate among classes of data items populating the records. Then you need to determine how destination table expressions will search the source table using the structured keys to return values to be used in the destination table. Speaking of source table and destination table, they can be separate tables to pull a value from one table into another. Or they could both be the same table to calculate a table in one value that's dependent on other items in the same table. For example, you could need the average among a set of items in a table that would depend on the sum of a common value among all such items in the same table. Another example, the quantity of an item in a table might be dependent on the quantity of another item in the same table. A CPU might need 2 NICs, so for all the CPUs allocated in a table, how many NICs need to be allocated in that table? The dest table structured key value searched for would be concatenated the same as the source table structured key values to be searched, and also using the same special character used in creating the source table structured key. Again, here are examples of concatenation expressions and values using same record fields and also literal values to search for. This OPI structure sequence continues in OPI structure part 2, table calculations.